Welcome to Push It to the Limit, the only TV series about mathematical series. I'm your host, Jake Singer, the Calculus Hunter. Tonight we're bringing you a very special episode about convergence or divergence. Allow me to explain. When a series converges, the sum of its terms equal a finite sum. But when a series diverges, the sum of the terms is not a finite number. Our producers have worked long and tirelessly to assemble a team of the best and brightest mathematicians from around the world. Let me show you what we've got. See here. Alright, let's let them get back to work. Tonight they will present to you 3 methods on testing for convergence and divergence. The P-series test, the direct comparison test, and the limit comparison test. Enjoy the show. We've spotted a wild mathematician. Look, there he is. Come on, let's get close. Be very careful. They're known to bite. I've just received word that 2 other mathematicians have just solved the code of the P-series.
So a P-series is a series with 1 over n to a power. And n increases as it approaches infinity. So the trick is that if p is greater than 1, the series is going to converge, and if p is less than 1, the series is going to diverge. But that does not include 1.
Come this way. Come over here. Come over here. Look at this beauty. Look at this beauty. No, not that. Right here. Okay, here, we've got an example. We've got the sum of 3 over n squared. See, in this case, p is equals 2, which is greater than 1, so therefore the series must converge. Here we've got another example. Another series, as n approaches infinity, of 7 over n to the 1/2. In this case, p is 1/2, which is less than 1. Therefore, the series must diverge. Incredible stuff we've got going. Incredible stuff.
Now for the direct comparison test. For direct comparison test and limit comparison test, we need a second series, b sub n. We find the series by taking the highest power of n in the numerator and the denominator, ignoring any coefficients and all other terms, then simplify. For the direct comparison test, if b sub n converges and a sub n is less than or equal to b sub n for all n, then a sub n also converges. If b sub n diverges and a sub n is greater than or equal to b sub n for all n, then a sub n also diverges.
And here, we have our direct comparison example. We have the sum from 2 to infinity of 4n squared plus n over the cube root of n to the 7th plus n cubed. And from that we find our b sub n to be n squared over n to the 7/3. And simplifying that, we get 1 over n to the 1/3. And because p is equal to 1/3, which is less than 1, by the p-series test, b sub n diverges. And because a sub n is greater than b sub n for all n and b sub n diverges, by the direct comparison test, a sub n diverges.
Here we are at Panera Bread, one of the greatest habitats for mathematicians, and a fine place to get a snack as well. Come in, I'll show you.
So now for the limit comparison test, you're going to take the limit of a of n over b of n. If the limit is positive, then the sum of a of n converges if the sum of b of n converges. And if b of n diverges, then a of n diverges. If the limit is 0, then the sum of a of n converges when the sum of b of n converges. And if the limit is infinity, then the sum of a of n diverges when the sum of b of n diverges.
Now for an example.
So, you have the series, the square root of 2n squared plus 4n plus 1 all over n cubed plus 9. You find b sub n to be square root of n squared over n cubed, which, when simplified, becomes 1 over n squared. Here you can see that p equals 2, which is greater than 1. So by the p-series test, the series b sub n converges. So now, you take the limit of a sub n over b sub n, which is the same as a sub n times the reciprocal of b sub n. So, when you solve through all the algebra and find the limit as n approaches infinity, you get 1. So, because b sub n converges and the limit as x approaches infinity of a sub n over b sub n is greater than 0, a sub n converges.
Exactly.